Welcome to the last lecture, the 7th lecture from the course Mathematical Finance. And this week we will be talking about models with stochastic volatility. And as background material, you can read chapter 16 and chapter 18 from Yoshi's book. So we've talked about quite a bit of models with option pricing and option pricing formulas and stochastic processes. And so far we have been using kind of nice stochastic processes to model underlying values and then to model the prices of options. And of course we started with the Black-Scholes formula, where we basically use geometric Brownian motion as a model for how the stock price moves through time, and geometric Brownian motion leads to normal probability distributions. We talked about these interest rate models, where we use these Gaussian martingales for interest rates, because interest rates can go positive and interest rates can maybe go a little bit negative. And maybe it's possible to use a little bit more general model, where you say, I model my martingale as some deterministic function of time sigma of t times the underlying process raised to the power gamma. And then basically for gamma is equal to 0, we have the Gaussian process. For gamma is equal to 1, we get this log normal process, and it is possible to kind of work out what the stochastic process is for different values of gamma, or for all the intermediate values of gamma. And this leads to a class of processes and a classes of probability distribution known as constant elasticity or variance, or CEV. So the question is, it's nice that we have these nice probability distributions, a log normal distribution, the normal distribution, or the Gaussian distribution. But are these nice mathematical distributions consistent with the prices of options that we actually observe in the market? And unfortunately, the real world is more difficult than our nice mathematical model. So actual option prices that we observe across a range of strikes in the real world does not conform to any of these nice distributions. But let's dive a little bit deeper into this. And I have downloaded actual quoted prices for options on the Dutch stock market index, the AEX index. So I have downloaded on the 18th of March, I have downloaded options on the stock market index. All these options expire on the 16th of September 2022, and that is 181 days. So this is roughly options with a half-year maturity. And website also says that the futures value or the forward value for the AEX index is 702.17. And here we see some quoted prices. Here is the column last, which is kind of the last price that was quoted on a particular day. And then we see for different strikes, so the forward value is like around 700. So I've quoted some strikes which are almost at the money, and then one notch below and one notch above. And then for each strike, you see the price for the call, which is in this case is 58.78. The price for the put is 36.56. And then for the 700 strike, you see a call and a put price. Then for the 720 strike, you see the call and the put price again. And again, when the strike goes up, the price of the call is going down. And obviously, when the strike price is going up, the price of the put is going up. And if we have these quoted prices for options, then we kind of substitute these into the Black-Scholes formula and then kind of check which level of volatility makes the Black-Scholes formula match these quoted option prices. Well, if you think about the Black-Scholes formula, what we need is we need to input the discount factor, and we need to input this forward price. And kind of a nice way to kind of back out what the price of the discount factor, or what the correct value of the discount factor and the correct value of the forward price is to use something that is known as put-call parity. And what does put-call parity say? It says if I subtract the call price for a given strike minus the put price for a given strike, so that difference between the call and the put price at the same strike, that difference is equal to the discounted value of the forward price minus the strike. Nice thing is I know the call price and the put price, I know the strike. The only unknowns that I have in this equation are kind of this discount factor, the forward price, but these are exactly the things that I want to know. But what I have done is for these prices here, for these quoted prices here, but then for a much wider range, I have plotted this difference of the call price minus the put price at given strike for a whole bunch of strikes. And these are basically all the strikes that are quoted for a particular day on that website. You see these dots are, as they should, because this is put-call parity, they are very close to a straight line. What I can do is I can do a regression. I can regress a constant plus beta times the strike on these C minus P prices, on these put-call differences. Then here is the regression line. In Excel, you have this nice feature that you can actually plot this Excel line. So the regression coefficient is minus 1.0091 times the strike plus 703.51. The value of alpha is this minus 1. The value of alpha is this 703, and the value of beta is this minus 1. And then if I match the alpha and the beta to this formula here, then I can identify that D of t is equal to minus beta. So the discount factor that the market is using to price all these call options is 1.00919, which is slightly above 1. For short term, so for the half-year period, we do still have a little bit negative interest rates at this moment. And the forward price is the alpha divided by minus beta, or alpha divided by capital D. That is the 702.17. And this 702.17 is, that's consistent with what the website says, that's what the futures value or the forward value is. Now that we have the discount factor and the forward price that is, let's say, consistent with how all these put and call options were priced, we can then input that into the Black-Scholes formula for the different strikes. And then the only unknown I have left is what is the sigma number that I should use. What I can now do is I can compute for each strike, I can solve numerically for which number sigma, which volatility number sigma for each strike K. So this is why I have this subscript K here. So for each strike K, I can solve for the sigma value that matches the theoretical Black-Scholes formula with the actual price that is observed in the market. So for these prices of 680, or for the strikes 680, 700, and 720, I observe those prices 58, 36, 46. Then I search numerically for which value sigma does the Black-Scholes call option value exactly match the market price. And then as a double check to see if there is maybe not something wrong or no inconsistencies, I have done this solving independently, both for the call option and for the put option value. What we should have, again, this is put-call parity, that the numerical value for the volatility should be exactly the same for the call and the put price. You see this is pretty close, 2411, 2411, it's 2150, 2150, and then it's 2289 and 2288. So you see there is a slight discrepancy here. Again, this is probably due to the fact that the quotes here are rounded to whole euro cents. But we do see that we are using these actual quoted prices here and that these numbers are very close. If I do this exercise for all the strikes from 400 to 1050, I get this implied volatility pattern. What we clearly see, and this is why this is called a volatility smile, you have this kind of downward sloping and then upward sloping graph of the volatility. And people in the market call this a volatility smile. What we also see is that the Black-Scholes formula that uses a log normal distribution is not consistent with the prices observed in the market, because if markets would say, well, the actual probability distribution of the underlying stock price is a log normal distribution, for all the strikes we would use the same sigma number. And we are clearly not using, or the market is clearly not quoting these option prices from a log normal distribution. It is using a little bit fatter distribution, or a little bit fatter tail, I should say, for lower strikes. So the market is kind of saying, relative to the log normal distribution, I am using a little bit fatter tail for very low strikes. So the market is kind of saying, for pricing options, we are using a little bit fatter tail for strikes that are very low or for prices that are going down. Then above a level of, let's say, around 850, so this is higher than the forward point. The forward point was around 700, that's over here. So in the middle of the distribution, the volatility is still going down relative to the log normal, and then for very high values or relatively high values from 850 up to 1050, the volatility, the implied volatility is slightly increasing again. So the market is kind of saying for very high values of the stock price or relatively high values of the stock price, we are also using a little bit more fatter tail than the log normal distribution again. I have done this for the September quote. So this is kind of an implied volatility pattern for September. So for options with the time to maturity of half a year. I've also done the computation for options with an expiry to May. So that's kind of a 3-month. Then you see that the volatility for shorter maturity options, this implied volatility pattern is a bit more pronounced. And that is typical that the smile is kind of more pronounced for shorter maturity options, and then it does flatten out, but it never becomes completely flat for very long maturity options. And the second thing that we see, if you would repeat this exercise at different time points, then you see that this implied volatility surface itself is also, so the smile shape is, let's say, you always see this type of smile shape, but the level of where volatilities are is itself also moving up and down through time. So these are indications that volatility itself is also changing over time. So if we want to get a better fit with observed option prices, we need to use a more sophisticated model. And basically, we need to introduce an extra source of randomness or multiple extra sources of randomness into our models. And two types of models that are quite often used are, you can either say, I kind of have this Brownian motion, and then I'm adding a so-called jump component to my Brownian motion. And then you have this idea that once in a while there is kind of a crash in the stock market. This crash in the stock market leads to kind of a discontinuous jump in prices. These are models known as kind of jump diffusion processes or variance gamma processes, and Yoshi talks about them in his book. And qualitatively speaking, the presence of jumps is very successful in kind of doing a very sharp smile for very short maturities. The problem is if you go to longer and longer maturities, you have this law of large numbers effect, and let's say the presence of jumps kind of averages out if you go to longer maturities. So the problem with jump type of models is that you are able to get a very nice smile pattern for very short maturities, but then if you let the model run forward and look at half-year options or 1-year options or 2-year options, the smile flattens out kind of too fast in these kind of jump models relative to the smiles that we see in the market. Therefore, I will focus on another type of models which are known as stochastic volatility models. Stochastic volatility models are not ideal themselves, because stochastic volatility models are able to produce kind of a consistent smile throughout the maturity. Then the smile is so consistent that if you go to very short maturities, the stochastic volatility model, let's say, cannot make the smile come as pronounced as we see it in the market. So if you would want to kind of combine both features, you would already need to go to a class where you can introduce a jump component to kind of capture the dynamics for very short maturities, and introduce a stochastic volatility component. Again, let's say this is a very fancy, very advanced class of models. I will focus in this lecture for now just on introducing a stochastic volatility component. And when you are interested, you can read about the jump models in the book by Hoshi. So the best known model for stochastic volatility, I will use the abbreviation SV for stochastic volatility, is the model by Heston, which was published in 1993 already. And what the Heston model does is introduces a new stochastic process, typically denoted by V of t, and that models the volatility itself as a stochastic process. And why is the Heston model so popular? It does allow for closed form solutions for the characteristic functions. So you can quickly compute the prices of options using these Fourier inversion techniques that we talked about in week 4. And the model is flexible enough to provide a reasonably good fit to the smiles of options that we observe in the market. How does the stochastic volatility, or how is the Heston model specified, is we have a system of two stochastic differential equations. The first one is like a Black-Scholes, and what I will do here, I will be directly modeling the Heston model under the risk neutral measure. So the stock price has a drift equal to the risk-free rate R. So if we would have a normal Black-Scholes model, then under measure Q, we would have that ds is R as dt plus sigma s dw. Now we're going to make the sigma a stochastic process, and the way we're going to model it is we're going to take the square root of this V process. So the square root of V is a stochastic process, and that is going to take the role of the constant sigma in the Black-Scholes model. What's the dynamics of the V process itself? It has this kind of mean reversion component. So I have a positive number lambda, which kind of says how quickly, if I get a shock away from the long-term mean, how quickly is my volatility process V being pushed back to this long-term mean? With lambda is very large, I get pushed back very quickly. And if lambda is a small positive number, I'll only get it pushed back very slowly. And then this theta is the long-term risk-neutral expectation of the volatility process far into the future. So this is kind of the long-term mean where the volatility process is being pushed towards. And the speed of pushing that is controlled by the parameter lambda. Then we have a so-called vol-of-vol parameter. So this is the volatility of the volatility process, and we will denote this by sigma subscript v. And then the v dynamics, it's not log normal, but we use this square root of v specification. These processes are known and have, let's say, we know what the probability distributions are of these type of processes. These type of processes are sometimes called Bessel processes. Also, they are known by Cox, Ingersoll, and Ross processes or CIR processes. We know that such a specification for the variance process with this square root leads to probability distributions that are equal to non-central square distributions. And again, you can also see this as an example of a constant elasticity of variance type of process where we take the stochastic process and then raise to the power 1/2. So it's kind of sitting intermediately between the normal distribution where you take v to the power 0, the log normal distribution where you would take v to the power 1. Here in these Bessel processes, we model the dynamics as v to the power 1/2. Reason for taking all these square roots here becomes, let's say, becomes more apparent in the next slide, because it turns out if you make this square root choice, then you have a lot of nice cancellations later on. So the VT process is guaranteed to be positive with this square root specification. We have this positive value for square root of v, and therefore we can use this as a driver for the volatility of the stock price process. We have two stochastic processes which are driven by two Brownian motions. We have a Brownian motion for the stock price, which is W superscript S. We have a Brownian motion for the volatility process, which is W superscript V. The Heston model allows for the fact that these two Brownian motions can be correlated with each other with the correlation parameter rho. So in total, there are 1, 2, 3, 4, 5 parameters in this model, and these 5 parameters you can choose to kind of calibrate the model to the observed prices of options. And the interest rate parameter is basically given by the outside world. So there are effectively 4 parameters, lambda, theta, sigma v, and rho, that you are free to choose. And obviously rho is a correlation parameter. So that is strictly between -1 and +1. And sigma v must be positive, and lambda must be positive, and theta must be positive. So if we have this more sophisticated specification of the stock price process, the dynamics of the stock price process basically becomes fairly, we don't have a explicit probability density function for the stock price in the Heston model. We can compute the characteristic function explicitly. So we can use these techniques from week 4. So how do we deal with the Heston model, or how do we solve the model, or how do we find the characteristic function? First, we're going to do this log transform that we already used for the geometric Brownian motion. And if we apply Ito's lemma, the logarithm of S, we get that the X process itself has a volatility term which just depends on square root of v, and then the dependence on x disappears, and then we get the Black-Scholes. We had r -1/2 sigma squared. Now we already see why the square root of v is a clever choice. -1/2 v that you see here is actually -1/2 the square root of v squared, because that's what Ito's lemma tells me. But the square root of v squared is v itself. The couple of processes we're going to be looking at is the combination of x and v. What we are interested in is to compute the characteristic function. This characteristic function is defined as the conditional expectation, conditional on the information at time small t, of e to the power I times xi times the process x at time capital T plus I times psi what the process v is at time capital T. So this is now a bivariate characteristic function for the two stochastic processes x at capital T and v at capital T jointly. However, we are typically interested in pricing equity options. So the payoff that we have will only be a function of the x variable. Therefore, we can basically set psi equal to 0, and then we kind of see the marginal distribution, or we are only interested in the marginal distribution or characteristic function x capital T only in the x direction, since we never have a payoff that explicitly depends on the v process. So that leads to a nice simplification, that we only want to only need to compute this expectation of e to the power hour I xi x of t. How do we do that? Well, here is a recap of the Heston model. We have the stochastic process for the x process, and we have the stochastic process for the v process. This conditional expectation is basically we are going to apply the Feynman-Cutch formula. Function phi at time small t of x and v, which is this conditional expectation, solves a partial differential equation. The partial differential equation is kind of similar to the Black-Scholes partial differential equation. I take the time derivative, so now the subscripts that I'm using are partial derivatives. I take the time derivative of the phi function in the t direction. And I take the drift term of the x process that is sitting over here times the partial derivative of the phi function with respect to small x. Then I take the drift term of the v process and the theta minus v, and I multiply that with the partial derivative of the phi function in the v direction. Then I need to do these double derivatives, and what you do, similar to the Black-Scholes formula or what you do with Ito's lemma, is I take 1/2 times this term squared. So again, I get this nice cancellation that square root of v squared becomes 1/2 times v. That is the volatility, the x process, or that's the variance of the x process. So I get 1/2 times v times the second derivative of phi with respect to x. Then I need to take care of the correlation term, and the correlation term is rho times the product of this term and the product of this term. Again, we see that the square root of v's multiplied together then become a v term, so I get rho sigma v times v. So this is the covariance term between these two Brownian motions. This covariance term I multiply with mixed partial derivative in the x and the v direction. And the last term is the variance of the v process, or the local variance of the v process, which is 1/2 times sigma v squared times the square root of v squared. So this is 1/2 sigma v squared v times the second partial derivative of phi with respect to v. That's it. So I have this partial differential equation here. And the boundary condition is that the phi function evaluated at time capital T. And then, of course, I don't need to worry about my conditional expectation, because when I am at time capital T, I should match this payoff here, which is e to the power I xi x. And I don't need to worry about the v because I've taken 0 times v. Again, when we solve the Black-Scholes equation, partial differential equation, it's not easy to solve partial differential equations. Here, in this case, we can use a nice trick with a fancy word you call this an ansatz. Basically, what you do is we try to guess a solution of the functional form of this function phi. And the solution that you are guessing is that phi as a function of t, x, and v can be expressed as e to the power function capital A, that is a deterministic function of time only, plus another deterministic function of time b times x, plus another deterministic function of time c times v. So this is called sometimes an exponential affine form. Take e to the power, and then you do this kind of linear form of a plus b times x plus c times v. The boundary condition at time capital T is that at time capital T, match e to the power I psi x, well then a at time capital T should be equal to 0, c at time capital T should be equal to 0, and then b at time capital T should be equal to I psi. Okay, so let's take this functional form here. Now we're going to substitute this guess for our functional form into the Heston partial differential equation. So what are all these partial derivatives? If I take this function here and if I take the derivative with respect to time, I first see this exponential. And if I take a derivative of an exponential, I get the exponential back. Then I should take the derivative of everything that is in the exponent. The time derivative of everything in the exponent is the time derivative of a plus the time derivative of b times x plus the time derivative of c times v. So that's this first term here. So this is exponential that you get back is the original function phi. Then I take the time derivative, and that is the time derivative of a plus the time derivative of b times x plus the time derivative of c times v. So that's this first term here, and that's this time derivative here. If I take an x derivative, it's even simpler because it's linearly in the exponent. If I take a derivative with respect to x, again, I get my function phi back. Then if I take the derivative of the exponent with respect to x, I simply get the function b back. That's this phi times b term here. Then for the v derivative, I get phi times capital C. And for the double x derivative, I get phi times b, so b squared. For the xv term, I get b times c. And for the phi vv term, I get phi times c squared. So that's great. It still looks like a god-awful mess here. But the first thing we notice is that I've made all these phi terms. So every term that I have here is now multiplied by phi. And for phi not 0, I'm being a little bit sloppy here. First thing we can do is we can divide all these phi terms out. Now, once that we do that, then we see a bunch of terms that are linear in V. I've made all them purple here. And what can I now do is, if this thing should be equal to 0 for all values of V, it means that if I collect all the terms that depend on V, and if I put that term or that coefficient sitting in front of V, if I make that whole coefficient equal to 0, then the dependence on V disappears. If I make the term that depends on X, which is just B of T, that is also equal to 0, so then the X dependence also disappears. Then if I collect all the constant terms, which is this term here, and this term here, and this term here, if I collect all these constant terms, and if I set them also equal to 0, then I have found an actual solution to this partial differential equation. That's the trick that I'm doing here, is first collecting all the V terms, which are denoted in purple here. So I get this C of T term, and then I get minus 1/2 times B, that's this term here. I get minus lambda times C, that's this term here. And then all these three depend on V, so I get 1/2 B squared. I get rho sigma V BC, that's this term here. And I get 1/2 sigma V term, sigma V squared C squared, and that's this term here. And here for this, I have included the time dependence of these functions here. If I collect, and then I say this thing should be identical equal to 0 for all values of V. So it means that if the combination of all these terms is equal to 0, I am basically solving the equation in the V direction. Notice this is now an ordinary differential equation in the functions B and C. So the functions B and C are not stochastic processes, they are deterministic functions of time. X terms is much simpler because there's only this one X term here. So the time derivative of the B function should be equal to 0. Well, if the time derivative of the B function is equal to 0, then the B function itself can only be a constant. I know that B must be equal to Ixi. So I've already solved what the B function is. The B function is equal to the constant Ixi for all values of t. If I collect all the constant terms, I get that the time derivative of A plus R times B, that's this term here, plus lambda theta times C, that's this term here, that should also be equal to 0. That means that the time derivative of A, that I can express A as the integral from small t to capital T of RB plus lambda C. Well, RB is equal to a constant. So that time derivative, or that integral from small t to capital T, becomes B times R times T minus T. So that's this first term here. And the last term here becomes lambda theta plus time the integral from small t to capital T of the function C of S ds. Why does this work? Well, if I take the derivative with respect to time of capital A, I am getting a minus Ixi R. And if I integrate with respect to the lower bound of the integral, I'm getting minus lambda theta times C of t. That, of course, is minus B, minus RB, so that will cancel against this term here. The minus lambda theta C of t cancels against this term here. And obviously, A at time capital T should be equal to 0, and if I set small t equal to capital T, then this term becomes 0, and this whole integral also collapses to 0. The only thing I've now left to do is to solve this partial differential equation. Again, function B, which makes it look rather horrible, is actually a constant. So if I substitute the constant Ixi, and remember that I is the imaginary number, into the order differential equation for C of t, I get a little bit simpler ordinary differential equation. I get that C of t is some constant times the function C itself, plus another function times the function C squared, minus a constant. So again, it looks rather long, but the ordinary differential equation is a nonlinear ordinary differential equation, but it is a solvable one, which is of the form some constant term times the function C itself, plus 1/2 times another term squared times the function C squared, minus 1/2 times another constant term. And it turns out this quadratic first order differential equation in C is a solvable ordinary differential equation. It has the following explicit solution. You get this expression with exponentials, and B is another number which is this term squared plus the product of this term here and the sigma v term squared. It's also out that you can integrate this function C of t explicitly, and if we substitute the integral of lambda theta times the integral over C of S into the capital A function, we get the following expression for A of t. It's a little bit long, but all these terms are very explicit. So, to summarize towards the end of the story, we have an explicit solution for the characteristic function of the Heston model. The characteristic function is the conditional expectation at time small t of e to the power Ixi capital T. This characteristic function can be expressed as e to the power function capital A, which is a function of xi and t minus t, plus this function c, which is a function of xi and t minus t, and I get this Ixi x term. And the value of v and the value of x that I have here are the values of the stochastic process at time small t. So this is kind of the information that I know. So at time small t, I know that the X process is at the value X small t, and the V process is at the value V small t. Then I am looking ahead at this conditional expectation or the characteristic function of where the X process is going to be at time capital T. And this expectation is solvable. It is this expression, so it is a function, the conditional expectation or the characteristic function of X at time capital T is of the form e to the power capital A plus capital C times where the volatility process is at time small t, plus ixi, where the X process is at time small t. The functions C and capital A have these explicit expressions that we have here. And we are basically done with the Heston model because we now have a completely explicit solution of the characteristic function of the X process under the risk neutral measure Q. And we can use this to calculate prices of options. Remember, we have done this log transform. The X at time capital T is the logarithm of the stock price at time capital T. If we use the characteristic function of the X process to compute the prices of call and put options, we can use this numerical integration trick that we use in week 4. But what you need to do is to use the discounted payoff of e to the, not s minus k, but use e to the power X at time capital T for a call option and k minus e to the power X at capital T for a put option. Again, we can use the Fourier inversion method from week 4, where we can use this kind of tilting with this extra parameter alpha. Again, what you learned in week 4 is that for a call option, you should choose e to the power minus alpha x, kind of make this thing not explode for x going to plus infinity. For a put option, you have to kind of, I think for a put option, you are okay. You don't have to do any lot of tilting here because if x goes to minus infinity, e to the power minus x is kind of a well-behaved thing and doesn't explode. But again, remember from the case from week 4 is for a call option, you need to use a positive value of the parameter alpha. But don't use a positive value for the parameter alpha for a put option because then you are making this integral explode instead of converge. So using these Fourier inversions, you can now compute with numerical integration option prices in this Heston model. And you can then do an optimization trick where you say, I can now take the remaining 4 parameters, the lambda, the theta, the SV, and the rho parameter. And I can search numerically for which combination of these Heston parameters take my option prices that I compute with my Heston model, make them fit as good as possible to the prices of the observed option prices. And you may guess where the case is going to go is I'm going to give you this Excel spreadsheet with these actual option prices that were quoted in the market. And then I'm going to ask you calibrate these parameters of the Heston model such that you fit the observed prices of call and put options as good as possible with those 4 parameters of the Heston model. That's it for this week, and I will stop the recording.